Thank you, everybody, for attending the TTC today. This is another year of technical talks, and appreciate everybody joining this morning, afternoon, or evening, depending on where you are. I'm Matt Hughes. I'm a research scientist at MIT, person who's probably spamming your inboxes most of the time with these messages. And today it's my pleasure to introduce Dr. Bikram Bhatia. He's an assistant professor in the Department of Mechanical Engineering at University of Louisville. So before he was faculty at UofL in 2019, he was a research scientist at MIT, where he was working on opto-thermal systems for CSP and radiative cooling applications. His Ph.D. was focused on waste heat recovery, harvesting, and nanoscale pyroelectric films. His bachelor's was in IIT Guwahati in 2008, and his PhD was from UIUC with Professor Bill King, if I'm not mistaken, in 2014. So now he joins us to talk about his work from his group, and we're excited to hear what research he's been doing recently. So the floor is yours, Bikram. Thank you.
Thank you for this introduction, Matt, and thank you all for joining. I'm excited to share some of the work that we've been doing in our group over these past few years that focus on systems that constitute our energy infrastructure, which is shown here in this Sankey diagram. So if you look at the left here, we have all these energy sources that constitute our energy infrastructure. And on the right is basically how this energy is consumed. So if you look at our sources of energy, we see that almost all of them, including nuclear, geothermal, natural gas, coal, petroleum, all of these essentially involve converting a fuel into heat and then using that heat either to produce electricity or consume it directly in residential, commercial, and industrial and transportation applications. So if you look at it broadly, you can see that heat is really the backbone of our energy infrastructure. It is utilized in a vast variety of energy systems. It could include heat engines, which involve our power plants, most of the power plants that produce electricity, even our internal combustion engines, basically are examples of heat engines. Heat pumps, which again are used in air conditioning and refrigeration applications in our homes and elsewhere. Heat exchangers, which are found in applications all the way from your laptop to in large industrial applications, and energy storage, thermal energy storage, which is really required moving forward for solving our energy problems in the future. So if you notice, almost all of these energy systems essentially have a fluid as the main heat transfer medium. So in the heat engine, you typically have a Rankine cycle, which basically involves water and water vapor, or you can have a Brayton cycle based on air or supercritical CO2, again, fluids, which can result in some challenges. So you have problems with scalability for heat engines, and also the efficiency is somewhat limited, especially for heat pumps that use refrigerants, typically CFCs, which have really high global warming potential. And also there are some caps with the efficiencies for heat pumps, and heat exchangers, which again typically involve two fluids, which can have problems, which sort of limit the maximum temperature you can operate them, and also can have problems with leakage and such. Same thing with heat storage. If you have typically a phase change media which goes from solid to liquid, there is a large volume change associated with it, which again can cause leakage and other problems like corrosion. So while these fluidic systems have demonstrated to be really effective and relatively efficient, there are some challenges that result from these fluids in these energy systems. So the question that we have been addressing in our lab is essentially asking, can we replace these fluid-based heat transfer media with something that's solid. And the reason why we want to do that is several-fold. In some application, it can allow you to have a much higher temperature operation, which is again directly correlated with higher efficiency. Also, you get rid of a lot of leakage problems, and again, if you're using solid refrigerants, you don't have to worry about their global warming potential. It's basically zero. And also, it allows applications that have that are much more accustomed or well suited for low gravity or zero gravity environments, where especially phase change can cause a lot of problems. So we've been working on a variety of systems in our lab. With the time we have today, I'm going to be focusing on two. One is the heat pumps, and the second one is the heat exchangers. So let me begin with our work on heat pumps. So we all are familiar that air conditioning and refrigeration accounts for a significant portion of our total energy demand. Most of it is met by vapor compression systems, which is a very mature technology, uh, which typically uses refrigerants that have high global warming potential. So that's a concern, and also its efficiency is sort of stagnated over time. So people have been looking at a variety of different solid state based heat pumps and refrigeration systems. There has been a lot of work done on magnetocaloric systems over the last 3 or 4 decades. And it's by far the most developed solid state heat pump technology out there, which basically uses a magnetic field and the resulting entropy and temperature change within a solid material to develop a heat pump around it. Then there is the electrocaloric effect, where you apply an electric field to a solid material, which results in an entropy or temperature change, which you can use for cooling or heating applications. And similarly, there's also elasticaloric, where you apply uniaxial tension or compression to a material, and that results in a temperature change, which again can be utilized in a heat pump cycle. So these are all great. As I mentioned, magnetocaloric has been developed by the most developed of these by far, but there are again some challenges associated with all of these. With magnetocaloric, it's the size of the magnets and the cost associated with it, so it hasn't been very economical. Although I think there's one commercial product out there based on magnetocaloric cooling. That's a wine cooler. Then you have electrocaloric, which has shown a lot of promise in the last few years. There has been device demonstrations which have shown high COP values and power densities. But again, it is mostly suited for applications that are small scale. So typically chip cooling kind of applications. It's not necessarily scalable. Elasticaloric has shown a lot of promise in the last few years. Again, it mostly utilizes NiTi alloy or nickel titanium alloy, which is put under tension and compression. Again, there have been some device demonstrations with promising performance reported, but the problem with these NiTi alloys typically is that they don't withstand a lot of tension compression cycles, so they have a finite fatigue life, and so they are not able to withstand millions of cycles that you would want from a commercial heat pump device. What we've been looking at is the barocaloric heating and cooling. So this is based on the barocaloric effect, which hasn't really received a lot of attention. It only started to gain prominence, I would say, maybe around 2019 or so, when there were some material studies showing impressive performance in some material systems based on the barocaloric effect, which is the entropy change or temperature change of a material when you apply hydrostatic pressure to the material. And so you can characterize this barocaloric effect by applying hydrostatic pressure. So we do so in our lab using this stress trig that is shown here, which is essentially a piston cylinder system. You fill it up with a barocaloric material. You have a thermocouple embedded in it, and we measure the temperature as we apply pressure. And so as you do that, the temperature of the material rises. You let it equilibrate, come to room temperature. And then when you release the pressure, you see that the temperature drops drastically, and then again, it sort of equilibrates with the environment. So you can do these material testing for a wide variety of materials. One representative result is shown here for a material known as wax, which is a thermoplastic elastomer. You can see operating around room temperature, you can get to around the lowest temperature is around 0 degrees Celsius. So it's a pretty substantial temperature change of about 27 degrees Celsius or so. So what caused us a rise in interest in this field, the field of barocaloric heat pumps and coolers, is the study that came out in 2019, which showed what is known as a colossal barocaloric response in plastic crystals. These are materials that have order disorder phase transition, which result in really large latent heats, which are shown here. The entropy changes associated with that order disorder phase transition can be really large. It's by far the highest among all the other caloric phenomena tested. And what was interesting was, for the first time, we were getting entropy changes that were on par with traditional refrigerants like R134A. And so that is what caused that excitement. But again, there are a lot of challenges going from this material to an actual device. There's problems associated with compressibility, also the flowability of the material with high pressures and so on. So there has been a lot of work on these materials with this solid-solid phase transition, but we've mostly been focused on looking at elastomeric materials, which do not have a phase transition, but basically have an entropy change associated with the entangling and disentangling of these long polymer chains in these elastomers. And specifically what we studied were thermoelastic elastomers, which sort of balance the trade-off between high entropy changes and temperature changes with the high thermal conductivity of the material, which is also something that you care about if you're building a device out of it. So most of the work in this field has been primarily focused on the material side of things, the solid state refrigerant, and rightly so. But there has been almost no work looking at the translation of these materials into an actual working device prototype. So that's something that we've been focused on. And we basically took this idea of the barocaloric material and combined it with a prototypical heat pump, which works on a reverse Brayton cycle. So you basically have a four-step cycle where you compress the barocaloric material, and which results in an increase in temperature of the barocaloric material. You interface it with the hot side, and you reject the heat, and then you release the pressure, which results in a sudden drop in temperature, and then you interface it with the cold side heat exchanger or cold side reservoir, completing the cycle. So you can go through this cycle several times and basically have a functional heat pump. So we characterize the performance of this heat pump, like most, using two key metrics. The first one we look at is the specific heating power. And in our case, we are mostly focused on the heating side. You can also operate it in reverse and really focus on the cold side and make it work as a refrigerator. But we, in our work, mostly look at the heat pump operation. So we define the specific heating power as the amount of heat that is transferred to the hot thermal reservoir over the cycle time of this reverse Brayton cycle, normalized by the mass of the refrigerant that we're using. And of course, we also look at the COP, which basically is the efficiency of the heat pump, which is again defined as a heat transfer to the thermal reservoir divided by the work input, which in this case is mechanical work, so pressure. So we first started off with modeling this device performance. We have three components. First is modeling the amount of work that we put in into the refrigerant. So this is mechanical work going into the compression of the material. We can use linear elastic theory, and we compare the normalized volumetric change of the material as a function of applied pressure. And from there, we can figure out, okay, how much work we put in. That goes in the denominator of the COP equation. Then we have the barocaloric response of the material. So how much does the temperature change of the material with applied pressure? Again, for this, we mostly use some phenomenological work that is reported in the literature, and also experimental data reported in the literature for elastomers, which do not have a phase transition. And we model the thermal transport basically going into the as heat goes into the refrigerant and out from the refrigerant using basic heat conduction and convection equations. So we have this finite difference model, which can basically numerically model the operation of the heat pump. So we can predict what the temperature cycles will look like for the refrigerant, and also for different hot and cold thermal reservoirs, and also predict how much heat is being delivered in each cycle at every time step. So using this, we can figure out what the specific heating power and COP of the heat pump is as a function of applied pressure, which is shown here. So we picked a material known as nitrile butadiene rubber, which is a common elastomer, widely available, low cost, as our material of choice, which already had experimental results reported in the literature. And so what we see in these plots is, if you look at the specific heating power, as you apply more and more pressure, you can imagine the temperature change or the entropy change of the material increases. And so that causes the specific heating power to increase with applied pressure. As you change, go from really low frequencies to higher frequency, you see that the specific heating power increases, and that's just because the number of cycles increases in a given time. But if you go to relatively higher frequencies, like 100 megahertz for our system, which was about 15 millimeter or about 2 centimeter in diameter, a piston core, and about 20 millimeter 20 centimeter in length, so an L by D ratio of around 10. You see that if you go to really high frequencies, the specific heating power starts to drop, and that's because you don't have, at these relatively high frequencies, you don't have enough time for heat exchange between the solid media, the barocaloric media, which is relatively low thermal conductivity, and the whatever heat transfer medium you have outside. So we were using the heat transfer coefficient of around 100 watt per meter square, or watt per meter square Kelvin for this model. For the COP, the results are quite interesting. So if you look at as a function of pressure, you see that the COP initially increases, and that's because, again, same reason. You apply more pressure, you have a larger delta T or entropy change. That increases the numerator of the COP equation, COP term. And as you keep on applying more and more pressure, the work input increases exponentially with pressure, which causes the COP to drop after a certain time. So there is really an optimal pressure that you need to apply to maximize the COP of a heat pump. And as you go to higher and higher frequencies here, because of the limited heat transfer time, the performance decreases. You obviously want to balance the specific heating power and the COP both. So what we did then was we really wanted to give all the material scientists, which again dominate this field, an easy way to translate their material properties into a device performance. Because so far, the way people report the performance of any of barocaloric cooling or heating is generally by reporting what is known as a material COP, which does not account for anything to do with the with the device itself. But obviously, the device design plays a big role. And so we did take our basically a prototypical piston cylinder model, and we simply made some assumptions and simplified our finite difference method to essentially give an equation for a specific heating power as well as COP. Basically, we used the one-term approximation for transient heat conduction. So if we are operating at low enough frequencies and we can neglect the temperature gradients within the barocaloric core, we get this equation, which these equations that not only capture the material properties, so you can see the bulk modulus here, the thermal expansion coefficient, thermal conductivity, heat capacity. So the material properties are there, but at the same time, you also have device parameters such as a device piston diameter, the surface area of that piston where the heat transfer is occurring. So and also the hot and cold side temperature. So all of these are included in these set of equations that allow us to predict what the specific heating power and what the COP of a device will be for different material systems. So we use this model and we essentially looked at what the effect of different material properties would be on the device level specific heating power and COP. And so one representative result that I show here is the SHP for nitrile butadiene and rubber as a function of thermal conductivity. As you would expect, as a thermal conductivity increases, the specific heating power as well as the COP increase, while all these other properties are held constant sort of for an imaginary sort of device. So we have this model that we can now use to essentially correlate all the material properties to actual device performance. And so the next step was essentially to build the device, which is what we focused on, which hasn't been done except for one work which did not report the experimental performance for some reason. But we wanted to do that. And so the reason we think this hasn't been done so far is primarily two reasons. One is we are applying really large pressures for these barocaloric devices. So we are applying on the order of about 400, 500 megapascals of pressure. So that's 2 orders of magnitude higher than what you typically have in a vapor compression system. So designing something that can withstand that high pressure is critical and it's not trivial. And the second problem is essentially extracting heat from the barocaloric core and back into the barocaloric core is tough because again, these are low thermal conductivity materials. So that is somewhat challenging. So those are the two key challenges we focused on, and we went again with a simple piston cylinder kind of idea with an elastomer as our barocaloric material, which we chose as nitrile butadiene rubber, which has a Poisson's ratio of around 0.5. So when we apply this hydrostatic pressure on piston, the pressure gets equilibrated within the solid media fairly uniformly. And so we focused on the core first. That's a key component. We picked natural rubber as our barocaloric material, which has been demonstrated to be a pretty good barocaloric material as reported in this experimental result shown from the literature. You can see if you apply around 250 megapascals of pressure, you get around 15, 16 Kelvin temperature change, which is pretty good. The second thing is the heat exchange from this core and into this core. So we did that using a helical heat exchanger that surrounded this barocaloric core. And we modeled the transient heat transfer from the barocaloric core when we apply pressure and how that pressure gets transmitted to the heat transfer medium around it, which in our case was ethylene glycol. And we looked at, okay, how does the temperature evolve over time as a function of different number of passes of the heat exchanger, the helical heat exchanger. And so based on these results, we said, okay, around 8 coils, 8 passes is good enough because we don't want to have a lot of thermal mass of the heat transfer media around the barocaloric core as well, because that slows down the performance and reduces the heating power. So we settled on around 8 passes for the helical heat exchanger. And then we went ahead and built it. Again, the key challenge, remember, is you need to withstand high pressure. So we decided that titanium 64 alloy, which is fairly well known to have really high strength and also has relatively decent thermal conductivity as a material of choice, which we used to fabricate this barochloric core um, using laser powder bed fusion. And that the fabricated part is shown here, and the core along with our manifolds are sort of shown here. So we really focused on the wall thickness of this heat exchanger, because we don't want the Ti-64 wall thickness to be um, too large, because then it impedes heat transfer, but also we didn't want it to be too thin, because then it won't be able to withstand the pressure. So we did calculate the hoop stress and determined that around 2 millimeter thick wall is good enough with a certain factor of safety for our experiments to design this heat exchanger and barochloric. So this is the actual assembly that we have for the barochloric heat pump in our lab. It basically comprises two constant temperature thermal reservoirs for testing. We have solenoid valves and peristaltic pumps that basically pump ethylene glycol at high and low temperatures through the barochloric core. And we also have thermocouples at the entrance and the exit of the barochloric core to measure the inlet and outlet temperatures. Everything is controlled by a DAC, and so we can time the cycles pretty well. We also have heat exchangers to mimic the heat load, heat being released to the hot side and heat being absorbed from the cold side. So the way this heat pump prototype works is you first compress the barochloric material while all the valves are closed. There's no heat transfer media flowing through the core. You apply pressure, the temperature rises. You open the valves and allow the temperature of the heat transfer media to rise as it passes through the barochloric core. And that heat is rejected through this heat exchanger and is returned to the hot thermal reservoir. We then close the valves and we release the pressure that causes the temperature of the barochloric medium to drop. We open these other valves from and to the cold thermal reservoir and allow heat exchange to the cold side thermal reservoir and basically release the pressure and repeat the cycle again. The experimental results from this heat pump operation are shown here. So in one of our experiments, we had a thermocouple embedded inside the barochloric media, and we measure the temperature as a function of time, which is shown here. You can see that as you apply, you apply pressure, you increase the temperature of the core, and you have a heat exchange step with the hot thermal reservoir from 2 to 3. From 3 to 1, you basically release the pressure, it causes a drop in temperature of the core, and you finally allow heat exchange with the cold thermal reservoir. So this is the one complete cycle. We also have experimental data for the inlet temperature of the ethylene glycol coming in and going out. You can see that there is the temperature of the leaving stream is higher than the temperature of the inlet stream. These are obviously transient. We kept for the purpose of this experiment, we kept the temperatures of the thermal reservoirs fixed, and we could change it within a certain range. So depending on the adiabatic temperature of change of the refrigerant material, we had a span of around 6 Kelvin or 7 Kelvin. Which is sort of actually you can see. So for the barochloric core, as you saw, this is for a pressure of around 250 megapascal. You can see that the barochloric media goes from around 285 to 305 kelvins, around 20 Kelvin. So that sort of sets the upper limit of the temperature span. And so we can change the delta T by controlling the thermal reservoirs to mimic whatever application we want to look at. So we did experiments as a function of delta T. The results that are shown here are for delta T of 1 Kelvin, 250 megapascal applied pressure, and a cycle frequency of 3.3 millihertz, and heat transfer flow rate of 500 milliliters per minute. So from this experimental time series data, we can extract what the specific heating power is. Like as I showed before, as you apply more and more pressure, you increase the specific heating power, which is what we see for all these experimental results. And when you look at the COP, you see that as you apply higher and higher pressures, the COP actually decreases, and that's again because we are in the regime where the denominator of the COP term, COP equation sort of dominates, where you the amount of work that you put in is dominant. And so as you go to higher and higher pressures, even though the entropy change within the material increases, the work input term also substantially increases. So you have a decrease in the COP as you go to higher and higher pressure. But at this lowest pressure setting that we tested, we actually measured a COP of around 4.2 with this commercially available material, which if you compare with the commercial heat pump, the typical COP is around 3 to 4. So even with this first prototype, we were able to report COPs that are competitive with commercial heat pumps. And we are really excited because this is just a first prototype. There's obviously a lot of device optimization that could improve the performance, and we are working on some of that. And also, we believe that if we use some of these recently demonstrated refrigerants that have a solid-solid phase transition, we can achieve COPs based on our modeling upwards of 15, based on existing demonstrated barocaloric materials. So that's the work on the barocaloric heat pumps. I will next move to our other work, which focuses on heat exchangers. All right, so our work on heat exchangers focuses on heat exchangers for concentrated solar power application. So CSP, if you're not familiar, is basically a way of generating power from by using sun's heat. So it primarily constitutes a field of mirrors known as heliostats that focus sunlight onto a receiver, which has a heat transfer media. To heat up the heat transfer media, this heat transfer media could be solid, liquid, or gas. And the US Department of Energy has looked at all of these three media over several decades now, including running pilot scale facilities, using pilot scale facilities. And they've determined that there are several challenges that you have with fluid-based media. So if they looked at air as a heat transfer media, that was work done by the Brayton Energy up in New Hampshire, I think. And there was also a lot of work done, which concluded that air has a relatively low thermal conductivity, and so it wasn't as competitive. And then there is also a lot of work with molten salts, which change phase from solid to liquid. But again, they have challenges associated with leakage and corrosion, some of the things that I mentioned earlier. But there was also a lot of work done on solid particles, basically sand, alumina silica sand, as a heat transfer media for CSP application. And over the several decades, they've basically zeroed in on solid particles as a heat transfer media as the best approach forward for CSP. So for CSP application, the key driving force here is that you can actually heat up a media, solid media in this case, and store it. It acts as an inbuilt heat transfer storage media. There's no latent heat associated with a solid, but you can just store the heat as sensible heat. and there's no volume expansion associated with it. So it's pretty easy to store. And you can go to relatively pretty high temperatures, so on the order of about 1,000 degrees or so. And so when you have to deliver power, you basically pass this hot sand through a heat exchanger and deliver, and you have a secondary fluid, typically supercritical CO2, which drives a power turbine based on the Brayton cycle, ideally at high temperatures to produce power. And so, as you can imagine, one of the key bottlenecks for this power tower kind of configuration for CSP, which is shown here, is the heat exchange from hot solid particles into the secondary media, which again is most likely supercritical CO2 for the Gen 3 CSP systems. And so that's a part that we really focused on. There are different kinds of heat exchangers that people have looked at. I will focus on two key ones that are most common and studied widely in the field. One is based on tube banks for this falling particles or gravity-driven flow, and fluidized bed-based heat exchangers. Each one has its own advantages and disadvantages. So for a tube bank heat exchanger, it's really easy to implement. It is perfectly compatible for a power tower kind of application. You can have a scalable heat exchanger based on your application. The problem though is that the heat exchange, or specifically the heat transfer coefficient from that solid particle into the tube wall, is not very high. So the overall heat transfer coefficients are low. On the other side, you have the fluidized bed heat exchangers. It can give you a much higher heat transfer coefficient, but the problem is that it is complicated to integrate with the CSP system and can have a lot of parasitic losses associated with it. So those are the pros and cons of each. We've looked at both. I'll start off with the work that we did on tube banks. So if you look at sand falling on a typical circular tube, which is a common configuration for our tube bank heat exchangers, you will notice that particles actually accumulate on the top. They are sort of stagnant and they form a void at the bottom, which obviously is not great for heat transfer. So that is one of the main reasons why the heat transfer coefficient from these hot sand particles to the wall is not very high. So we looked at this problem in our lab, and we built this experimental test rig, which is shown here on the left. We have sand on the top. We have our test coupon, which basically involves a 3D printed coupon of the heat exchanger. We are mostly interested in the solid particle to tube wall heat exchange. So that's the part, because that's the bottleneck. So that's what we've really focused on. And so we use these test coupons to study that for this gravity-driven flow over these tube bank heat exchangers, essentially. We did high-speed imaging of these falling sand particles around these tubes. And based on that, we can actually track different particles and figure out what is the velocity around the tube for different kinds of heat exchanger configurations. So we looked at different tube geometries, including circular tubes, which are most common in the industry. We also looked at these diamond shapes and hexagons, which have been reported in the literature before. They were shown, or they were the claim was that their performance is better, can be better than the circular tubes. And this airfoil shape structures that we came up with, again, inspired by airfoil wings that are there in aircraft. So based on the literature, so we came up with this airfoil geometry for this heat exchanger, and we measured the velocity. So these are the values shown here are near wall velocity. So around 10 particle radii around the central tube wall. Using PIV analysis, we measured the velocity around these tube walls for all these different geometries, and we can see that it is shown here as a function of angular position. So if you look if top is 0 degrees, you see that for circular tubes, right on the top and right on the bottom. So on the top, you have a stagnant region, you have low velocity, and on the bottom, you have void areas. It's almost zero velocity, but on the sides, you have this large velocity as you have streaming flow along the sides. You kind of see slightly different behavior in this diamond shape lattice structure, where you have a much larger void area on the bottom. Um, and you have much lower velocities on this slopes. And hexagons are quite interesting. You have really high velocities along these sidewalls, again, which is a streaming flow as the particles rush through. But you have, again, a large void area on the bottom again. Airfoil geometry is actually quite interesting. We were for some reason expecting the velocities might be much higher for airflows. And what we had in our back of our head was that the higher velocity, a streamlined flow, will result in a higher heat transfer. But the velocities were lower, but the variation in the velocity along the angular position was not that significant. So that we thought was pretty interesting. We also modeled this behavior using Eulerian Lagrangian model, basically discrete dense phase particle modeling. All right, so yeah, you can see the modeling. It mimics the experiments pretty well. We see the same thing for our airfoil geometry. Relatively low velocity, but more uniform across the angular domain here. So we took that model and we added the energy equation to the model and mimicked the CSP operating conditions, and we evaluated what the particle to wall heat transfer coefficient was. So we kind of went into this expecting that the higher velocity, the job configurations that give us higher velocity will give us higher heat transfer coefficient, and maybe that's possible true for some of the regions, but on an average, we see that the airfoil geometry actually gave us a much higher heat transfer coefficient. That it has to do with the kind of flow that it promotes. So it promotes really a collisional flow, where the particles move sort of much more uniformly around the coupon, whereas all these other geometries had streaming flow, where you had sort of blockages in some parts, and then you had free flow in other regions of these coupons. So that is why that is what we think explains the higher heat transfer coefficient of the airfoil relative to these other geometries. And so this was great, but still the tube bank heat exchanger is not the ideal in terms of heat transfer coefficient, as I mentioned. So the other configuration that we could look at was the fluidized bed heat exchangers, which people have looked at, including a lot of people in industry. The challenge here is, again, twofold. One is that integrating a fluidized bed heat exchanger in a CSP power tower configuration is not quite straightforward. And the second and more interesting from our viewpoint is really characterizing the heat transfer from a fluid in a fluidized bed heat exchanger system, which has where the flow is really stochastic, and it's difficult to predict. So that is something that we were interested to study. So the first thing that we did was we actually created this multi-stage moving bed fluidization heat exchanger system, where we built a setup with 3 stages, where the sand came in and then was fluidized through these air inlets at each of these stages. And we looked at the particle flow around these tube walls as it went through different stages. And also, like, we have these air inlets on the bottom. So note that they have a sort of a cap on the top, which is quite typical in fluidized systems. So to prevent the sand from blocking these air inlets, which almost cause the sand to flow in a clockwise direction. So they have this interesting directionality associated with it. So like before, we did high-speed imaging and focused only on the near wall region and basically around 10 particle radii around the tube wall. And we calculated what is known as a granular velocity. So this is essentially the velocity of the particles in this near wall region as a function of the angular location of the particle. And we evaluated what the density of these sand particles are in that particular region um, in our experiment. So it is obviously a function of time, which is sort of what you see in the video that's playing on the left as a function of angular location. It is fluctuates quite a lot, and so that was sort of our challenge, is to understand how does this correlate with the heat transfer to this tube wall. And so to understand that, again, it's really hard to uh, develop a heat transfer coefficient measurement experimentally, um, a local heat transfer coefficient measurement for these granular systems. But we looked at a simple, as a first step, looked at a very simple volume of fluid model, which also gave us a granular velocity and granular density, which had magnitudes on the same order as the experiment, but it was a much simplified model. We could run it for a wide variety of parameters based on the experiments, and also we validated these results while not uh, perfect in the time series data. And I would argue that it's not possible to have one-to-one match with a granular system that has a flow field that is so stochastic in nature. But the magnitudes were similar, and we validated it based on experiments that were reported, one or two experiments that were reported in the literature, and also using more high fidelity DDPM based models that captured in our entire physics. So we use this model, including the energy equation, to predict what the local heat transfer coefficient is. So that's heat transfer from the sand, hot sand, to the tube wall as a function of angular location. And we sort of average it over time. And that's kind of what you're seeing here. So the horizontal narrow bars sort of represent the mean. The red bars represent the standard deviation, one standard deviation, and the total range of the measurements that we got from this model are represented by these large bars, vertical bars. So what we really wanted was the heat transfer coefficient from our experiment, and we argued that okay, the model is not high fidelity enough, but it does capture the basic physics of the particle flow for the two-phase fluid flow around the tube wall. And so what we did was we input tube geometry and other parameters like air velocities, as well as the granular velocity and granular density that we got from the momentum part of the model, momentum transport, so by solving the momentum transport equation. And as the output, we gave the heat transfer coefficient. And so we had several million data points that we got from this quick simulation that we could do. And we trained a random forest model that basically essentially gave us a function that allowed us to map experimentally measured parameters such as the granular density and velocity that we had from our high-speed experiments. And we asked it to predict the heat transfer coefficient, which it did, which is shown in this plot here. And it looks pretty interesting. You see first that there is some asymmetry associated with, well, the magnitude is conforms with what you would expect probably for a fluidized bed heat exchangers, and also it is in accordance with the DDPM model, the high fidelity model that we ran for the same experimental configuration. But you see this asymmetry, which was not there really in our training data, that we see in the experimental result, which we were actually quite happy to see, because in our experiment, as I mentioned earlier, we do have this asymmetry in our experimental setup, where the air actually forces the sand to flow in this clockwise direction. So you have slightly higher velocity on the left side versus the right, which is what we see in our heat transfer coefficient data. And we really see four regimes, even in a fluidized wet systems, for this heat transfer coefficient. You have the top regime, which still, despite the fluidization, you still have a narrow stagnant zone. And then you have this high velocity, high mixing area on the vertical edges. And on the bottom, you have a periodic stagnation and these large voids. And also you have some high velocity mixing on the other vertical wall, which gives you relatively high velocity and high heat transfer coefficient, but not as much as what you see on the left hand side. So that sort of excited us, and we're working towards looking at more configurations and mimicking different hierarchical structures for different kind of heat exchangers based on this approach. So with that, I would I'm here at the end of my talk. Just to summarize, our group is really focused on working on energy systems that basically try to replace the fluidic-based heat transfer media in different energy systems and replace them with solids. The work that I showed you today focused on a heat pump that uses the barocooler effect in solid media for heat pumping. And I also showed work on solid particle-based heat exchangers, which typically for CSP applications. But again, all this work can have applications in a wide variety of areas, including HVAC and refrigeration, energy generation, as well as thermal energy storage. So with that, I would thank my students, specifically Naveen Veerasekara, who led the work on the barocooler heat pumps, and Julio Izquierdo, who led the work on the solid particle heat exchangers, my collaborators, and funding support. And with that, I'll be happy to take any questions.
Great. Thank you very much, Bikram, for the nice talk. Now we have a few minutes for some Q&A. So if anybody would like to raise their hand. Oh, yes, I see a few. Maybe we can start with, I'll just go down on my list. Start with Jonathan, I think is the first one on my list. Oh, sorry. Let me, I think okay, now you can try to unmute. I think I had a...
Okay, thank you. That was my first time seeing a mute lock feature, so I'm getting used to that. Yeah, thank you for the really interesting talk. I had a question on the barocaloric heat pump. You were saying a big motive of what you're doing with replacing fluid systems with solid systems is minimizing leakage and fluid flows. But if I saw it right, you still had to have a heat transfer liquid, having an inlet and outlet to your system, and there was still a very high hydraulic pressure being applied to your rubber. So like I guess in its current form, is it actually less fluidy or less complex than existing heat pumps? And what are you envisioning in the future to either make it simpler or to increase the COP beyond that of existing heat pumps?
Thank you for that good question. So we actually, when we did the model, we were very cognizant of the fact that we do have a fluid in our system, which is ethylene glycol when we did the experiment. But for our model, we only model the heat transfer coefficient as on the convective side, which sort of, we were very intentional that we want to make it agnostic to what the heat transfer medium is on the other side. So theoretically, it can work, maybe not as well, but theoretically, it can still work if you have a contact heat exchange mechanism, right? A solid-solid contact. That's definitely doable. But obviously, to get the best performance for our experimental prototype, we stuck with ethylene glycol, which is, as you mentioned, a fluid. But I would say that the advantage this still has over regular heat pumps is that it doesn't have a two-phase flow, which is what you typically have in a refrigerant, right? So it does eliminate that part, which is really complicated, as you well know. Right, so that is something that I would highlight. The second thing, to address the high pressures and what I think will be the next step in this field, is really what we demonstrated were systems that were based out of commercially available, really low cost materials, so rubbers. But what we are excited about is not really these materials. There are other materials that I mentioned. There's a lot of work on plastic crystals, which can actually reduce the amount of pressure that you need to achieve the same amount of delta T or entropy change. They are a lot more compressible. There are some challenges because they tend to flow if when you apply these pressures. So there are chemists working on that material system, and a lot of other material systems that can allow you to go to uh, get large delta T's even with like an order of magnitude lower pressure. So all those can really simplify the performance. And also I would mention some work we can do on the system level where rather than having just a single piston cylinder system, what I showed, we actually have ongoing work where we have a series or parallel configuration of these heat pumps to essentially make it scalable, which improves the COP substantially, uh, uh, just from a system level.
Okay, thank you.
Great. I see Florian also has his hand raised.
Yeah, thank you. Do you hear me well?
Yep.
Yes.
Okay. One question on the barocaloric heat pump. If I understand well, the heat is made by weaving and unweaving this long chain of polymer. If that's the case, how can you replace this cylinder by a stack of thinner film of polymer, for instance? Can you reduce the thickness of the entire thing and maybe stacking them? Is that doable in your?
Can you explain a little bit more how?
Yeah, instead of having a single rod of polymer, can you have a stack of, I don't know, a millimeter thick disc, and then you could make a stack of this and compress this stack. Do you get the same efficiency at the end?
Right. So if you I guess go back to maybe the model that I showed, there are essentially three parts that you have to think about, right? There's a force, there's a barocaloric response, and there's a thermal transport. So if you have a stack maybe interdigitated with some high thermal conductivity media, that definitely helps the thermal transport. You have to ensure that the pressure gets transmitted uniformly, which is a challenge in some solid media because the Poisson's ratio is not 0.5, so they're not always very compressible, so the pressure doesn't get transmitted. If you are able to transmit the pressure uniformly, the barocaloric response is going to be similar. And if you have a system configuration that allows you to improve the thermal transport, that's definitely a plus because that's one of the biggest bottlenecks for the device performance of a heat pump. So I would say yes, if you can look at different device architectures, there are ways you could improve the overall performance. Hopefully that addresses your question.
Yeah, thank you.
Thank you.
Okay. I see Akanksha has her hand raised, so yeah, please go ahead.
Yep. Thank you, Bikram, for the nice presentation. I had a couple of questions. So you said for the model that you had, it's all on the barocaloric. The model that you developed, you said you used the one-term approximation, right, for that transient model. So that's valid, like within a certain range of Fourier numbers. So did you check what does that correspond to in terms of like your cycle times, and is that still like realistic from the application standpoint?
Yes, that's a wonderful question. That's my student and I spent about 6 months on answering that question. It is we did look into it. It definitely narrows down our frequency range where we can operate. We cannot operate obviously at higher frequencies. But if you looked at the frequencies that we're currently operating at, which is like in the maybe 1 megahertz to hundreds of megahertz range, I think the one-term approximation, if I remember correctly, limited us to maybe like 50 millihertz or so. So not all the way up to 100 millihertz, but pretty close. And at the same time, it gives us a ballpark as to what the performance is going to be in a relatively easy manner, right? We just have an equation.
Right. Yeah, just to
Wonderful.
get that like closed form solution. I mean, another question I had was, is there, I don't know much about the barocaloric materials, but did they experience any kind of hysteresis if you do, hundreds of cycles with these materials?
Yes, that's another very good question. So there is a lot of work that the material scientists are doing on hysteresis. The typical and this hysteresis is particularly a problem for the materials that have an order-disorder phase transition, which remember are the materials that we're most interested in. But that was another reason why we did not choose or at least as a first step to go into using these materials with solid phase transitions, because the hysteresis is substantial, like on the order of about 10 Kelvin when you have your delta spanners, 30 Kelvin or so. So it's pretty substantial. In elastomers, the hysteresis is relatively low. The fatigue life is decent, although there hasn't been, well, the fatigue life has been tested for elastomers for a wide variety of applications, not necessarily for barocaloric, but the performance is decent and the hysteresis is relatively low compared to materials that have disorder transition. That being said, there are a lot of chemists and material scientists who are working on reducing this hysteresis. They think it has to do with the hydrogen bonds being broken and reformed as you apply pressure. So there are reports of lower hysteresis materials that are being reported like almost every other week now these days.
Got it. Thank you.
Great. Well, we're a little bit past time, so if there are no other burning questions, I think we can wrap up for today. So yeah, let's thank Bikram again for his nice talk, and we'll have another TTC actually next week with Alison Mavi, who will be working on presenting her work on annular flow. So I'll present an invite for that, and we'll have another one a few weeks later. So yeah, hope you all doing well and have a great rest of your day. So thanks.
Thank you, man.
Thank you.